Yeah, so today we will see this design of bearings, right? So before going into those design equations and all, first we should have an idea that what a bearing is. So a bearing is actually a particular component which permits the relative motion between two parts, right, without much friction between them. So generally it is used between shaft and housing of shaft, right? So if we discuss about main functions of bearing, then we can list those functions of bearings, right? So if we list functions of bearing, then it is actually bearing ensures free rotation with minimum friction. Free rotation, right, with minimum friction. Right, then it also supports and holds, right, the shaft in correct position. It supports and holds, right, the shaft in correct position. And it also take up the forces acting on the shaft and transmits it to the frame, right? So the bearing also takes up the load and transmits it to the frame, right? So this is the main function of bearing, right? Bearing may be classified based on various criteria. So one of the criteria to classify the bearing is, as we have mentioned here, that it can take up the load acting on the shaft, right? So if the load acting on the bearing is in the radial direction, right, then it is considered as radial bearing, as it is mentioned in this figure, right? While if the load acting is in along the axis of the shaft, as we can see in this figure, then it can be considered as thrust bearing. So based on the direction of force, the bearings are classified as radial bearing and thrust bearing. Similarly, based on the type of contact, it is classified as rolling contact and sliding contact bearing, as it is mentioned in this figure, right? Here these are all rolling element, as it is mentioned here, right? So in this there will be line contact. So if that roller will be there, then there will be a line contact, and this is rolling contact bearing, because it will this roller will have rolling motion and it will perform that function of a bearing as mentioned here. It will allow the motion of this shaft with minimum friction with respect to this housing. Similarly, here sliding contact bearing, there will be some sliding friction. So here, in case of sliding contact bearing, as we can see in this figure, there will be this bush, and it is also known as journal bearing, right? So this journal will have a film of that lubricating oil between this housing and that journal, so it will allow its motion without much friction between them, right? So this is how the sliding contact bearing and rolling contact bearing is there, right? So we will see this different types of bearing, right? If we now first start with rolling contact bearing, then rolling contact bearing is also known as anti-friction bearing, right? because in case of rolling contact bearing there is not much friction, while in case of sliding contact bearing some friction is present when we start that shaft, right? So here in case of rolling contact bearing, it is that is why it is known as that anti-friction bearing, right? If we go for the different types of rolling contact bearing, then it is mentioned in this figure, like this deep groove ball, this deep groove rolling contact bearing, or cylindrical roller rolling contact bearing, or it is based on the shape of that rolling element, right? So angular contact bearing, self-aligning, and the spherical roller or taper roller or thrust ball bearing. So here in this rolling contact bearing, mainly four components are there, that rolling element, then outer race, inner race, and then cage, right? Housing all these elements. So this is how there are the construction of this rolling contact bearing and types of this rolling contact bearing. Here also there is a different capability of taking up the load of these different types of bearing. So in case of this deep groove ball bearing or this angular contact bearing, it can take that radial load as well as thrust load both, right? While some particular type of bearings cannot hold the radial load, maybe this particular thrust ball bearing can only take up the thrust load, right? And this way, based on the application of this bearing, different types of bearing are employed in different machineries, right? So after that, this is regarding that self-aligning. Actually, this is self-aligning principle, right? As we have seen that self-aligning bearing is there. So what happens in this particular case is, as mentioned here, the shaft is aligned with the bearing as shown in this figure A. But what happens is, in some of the application, the deflection of shaft may take place, right? As shown in figure B, you can have this deflection. So if you enlarge this, then there will be some this deflection alpha, right? So while this kind of application is there, when the shaft can be deflected through a particular angle, at that time, if this self alignment bearing is not there, then there may be some what we can say wear of the bearing elements and all. So in this application, we are using this self aligning bearing as shown in this figure C. So as and when this shaft is going to deflect, this bearing element will also going to take its what we can say alignment along the shaft axis, as it is shown in this figure C, right? So this is how self-aligning bearing is used for those applications where shaft may have certain deflection, right? Then there is static and dynamic load carrying capacity, right? Whenever we are designing these bearings, these two important things are there: static and dynamic load carrying capacity. If you see one by one, then let us see first this static load carrying capacity, right? So what do we mean by static load carrying capacity? So actually static load carrying capacity means this static load is the load acting on the bearing, right, when the shaft is stationary. Right, so here actually whenever we are talking about this static load, then because of this static load, there may be some deflection, right, or total permanent deformation of ball and that cage or that inner race can happen, right? So in case of this static load, for the maximum deflection allowed, right, or total permanent deformation allowed because of this static load is generally of the order of only 0.0001, right, of the ball diameter, right, in case of ball bearing, for example, right. So in case of ball bearing, the total permanent deformation allowed due to the static load is in the range of this 0.0001 of the ball diameter, right. So now based on this, first we need to check this Tribex equation, right. So we will again come back to this dynamic load carrying capacity later, but by having idea about this, what is static load and what is this permanent deformation and what is the static load carrying capacity, we may first discuss the Tribex equation, right. So let us see what is this Tribex equation. So as the figure suggests, or the figure A in particular, right here you can see this static load C naught is applied on the center of this particular what you can say shaft axis, and these are all the ball bearings, right, is mentioned as this P1, P2 and P3, right. So as you can see in this figure, only that this inner race is considered, right. So there are certain assumptions while deriving the Tribex equations, right. So let us first note down the assumptions, right, for this Tribex equation, that the races are rigid and retain their circular shape. Inner race and outer race, right, the races are rigid and retain their shape or circular shape, right, and the balls are equally spaced. And the balls in the upper half do not support any load, right. So only this lower half is considered, right. As we can see, the balls in the upper half do not support any load, right. The balls in the upper half do not support any load, right. So these are some of the assumptions, right, while deriving this Tribex equation. We will also see what this table suggests, right. We will discuss it, right. But before going to the table, first let us see what are the forces acting. So if you see, this C naught is the static load applied. So because of that, this reaction from all this ball is shown as P1, this P2, P3 similarly, right. So if we go for that forces acting in vertical direction equals to 0, this equilibrium will give us the C naught equals to P1 plus 2P2 cos beta plus 2P3 cos 2 beta, right. Now here in figure B, we are shown this deflection because of this static load. So this particular, here it is exaggerated, actually not this much of deflection may be there, but for the sake of understanding, they have shown that it has deflected from this O through this O dash, right. So because of that, this ball will also, or this inner race will also have this deflection of delta 1, right. So at P1 the deflection is delta 1, while at P2 this deflection is delta 2 as mentioned here. So if you observe, then there is what you can say, the angle between this delta 1 and delta 2 is that beta. So delta 2 can be represented as delta 1 cos beta, right? So if you exaggerate this view, then this will be delta 2, right? And this may be delta 1, right? So this may be entity, this may be this beta, right? Actually one more we can draw it clearly, right? Like this. This delta 2, delta 1, this beta, and this is 90 degree right here. So that is why this projection is then delta 1 cos beta, right? This will be this 90 degree. So that is why this delta 2 can be represented as delta 1 cos beta. So it gives delta 2 by delta 1 as cos beta, right? Now these are all based on those Hertz equation, right? Because context stresses are there in this particular application, right? So based on that Hertz equation, this delta is proportional to this load of this P plus 2 is 2 by 3, right? So for all the balls we can use this particular relation between deflection and load applied. So that is this delta 1 is equal to C1 P1 raised to 2 by 3, similarly delta 2 is equal to C1 P2 raised to 2 by 3, and so on, right? So if you have this, then this again delta 2 by delta 1 can be mentioned as this P2 by P1.
Sir, can you please repeat the step?
Sorry?
Can you please repeat the steps?
So here this particular deflection is proportional to this load, right? Or that support relation, that P1, P2, whatever is acting, right? Here, this one, right? So this deflection is proportional to this load raised to the 2 by 3 according to Hertz equation. So now we are using that particular relation, right? This is Hertz equation. From that we can have this relation, right? So now if we apply this to this deflection at different wall, right, then we can come up with this relation that delta 2 by delta 1 is equal to this P2 by P1 raised to 2 by 3. Okay, and as we have already derived that delta 2 by delta 1 is cos beta, right, from the geometry. As we have seen here, this delta 2 by delta 1 is cos beta, right? So if we apply that, then this cos beta will be equal to P2 by P1 raised to 2 by 3. So now we can write that P2 is P1 cos beta raised to 3 by 2. Is it clear? Hello?
Yes, sir.
Okay, similarly if you go for P3, then in that case this angle is cos 2 beta. So then you can derive the similar way that P3 is equal to P1 cos 2 beta raised to 3 by 2, right? And once you have the value of this P2 and P3 in terms of P1, then in this particular equation you can have the values of P2 and P3 written in terms of P1. So if you put the values of P2 and P3 into this equation, then what we can have here is this C0 equals to this P1 plus 2 P1 cos beta raised to 3 by 2, right, into cos beta, because it was 2p2 cos beta, right? So we have put the value of p2. Similarly, value of p3 is p1 cos 2 beta raised to 3 by 2, and again cos 2 beta will be as it is, right? So we can simplify it as C0 is equal to P1 into M, where M is nothing but this 1 plus 2 cos beta raised to 5 by 2 plus 2 cos 2 beta raised to 5 by 2, and so on, right? Now this beta is equal to 360 by Z, right? Why? Because beta is the angle, as we have seen earlier, and Z is number of balls. So as those balls are equally spaced, this beta is 360 by Z, right? So here, as that particular those balls are equally spaced, this beta can be given as 360 by Z, right? Now that table comes into picture. If we go for this beta is equal to 360 by Z, right, then if we put the value of Z as 8, and if we calculate the value of that M, what is M that we have derived here, right? This is M, right? So if we put the value of Z as 8 and then calculate beta, right, by putting the value of Z, then calculating beta, and then calculating M, it will give us this value which is mentioned here, right, for M. Similarly, for Z is equal to 10, M is this, 12 it is this, and 15 it is this, right? So if we now write that ratio of the Z by M, then it is coming about this 4.35, 4.38, 4.36 and 4.37. So basically this Z by M can then be considered as approximately equal to 5. So if we take that Z by M approximately equal to 5, then our C0 is equal to P1 M, right? So M, if we take Z by M as approximately equal to 5, then M is Z by 5, right? So C0 can be written as Z by 5 into P1, right? And where P1 is represented as this KD square, right? So this is how you can calculate the static load carrying capacity of a particular this bearing, right? So this is how you are having the static load carrying capacity, right? Now we also had written here that dynamic load, right, along with that static load. So now what is this dynamic load carrying capacity? So this dynamic load carrying capacity so basically whenever this particular capacity is defined as whenever any radial load bearing is there, then the capacity of bearing is defined as the radial load in the radial bearing, right, that can be carried for a minimum life of 1 million revolution, right? So this should be considered as this dynamic load rating, right? So basically whenever the bearing is in operation, then actually this load rating or that actual bearing life or L10 life is considered, right? So it is basically 90% of that ball bearings, right? It is the life where that 90% of balls are actually able to complete that number of revolution without the first evidence of any crack in it, right? So this is how we are having this dynamic load carrying capacity. So in this particular what you can say this actually, when if we consider only 50% of component of this ball bearing, right, then this life is much higher than this L10 life, but it is not advisable, right, because these bearings are used in some critical applications, and also at least 90% of the component must complete that much amount of revolution, right, or that much hours of its service, right, in whatever way you are defining it, right, before going through the first evidence of any failure, right. So this is how we are having this static and dynamic load carrying capacity, right. So in this particular uh, case, actually, then what sometimes adopted is they are coming up with this equivalent dynamic load, right. So this for equivalent bearing load, so it will consider this radial load as well as axial load, right. So here this P is this equivalent dynamic load, right. So x and y are radial and thrust factors, right. X and y are radial and thrust factors, right, while this Fr is radial load and Fa is axial load, while this V is race rotation factor. So it is generally considered as 1, right, when this inner race is stationary, right, and outer race is rotating, right, and 1.2 when outer race is stationary, right, and inner race is rotating. So generally it is considered as 1 only, right, this V, that race rotation factor, right. So yeah.
1.2 trace test factor when we consider, sir, what are the applications? Most of times we take V equal to 1.
Yes, most of the time this inner race is stationary. So in some of the application it is required that outer race must remain stationary, right. So in those case this 1.2 is considered, right. Otherwise this V is taken as 1 only. Okay, so if we take that V as 1, then our equation is simplified as this x Fr plus y Fa, right. So in that case sometimes only radial load is acting, right. So in that case then P will be equal to xFR, and if only axial load is there, then the P will be equal to YFA, like that we need to consider, right. So once we have idea about this, then there is one more important thing is this load life relationship. So if we consider this L10 life, right, then it is represented as this C by P raised to n, right? Well, this n is equal to 3 for ball bearings, and it is 10 by 3 for roller bearings. Right, now the C is nothing but dynamic load capacity. Right, so if you rearrange that equation, then you can write that dynamic load capacity can be represented as this load into that L10 life is to 1 upon n. So for ball bearing it will be this P into L10 plus to 1 by 3, right, for ball bearings. Right, while for other this roller bearings it will be P into L10 plus 2.3, right, for roller bearings. Right, so this is how you can have that relation between this dynamic load capacity and that load, right, which is acting on the bearing. Now in case of this in mentioning it with this rated bearing life in hours, or the relation with this rated bearing life in hours, there is one more relation, right, that is L10 equals to the 60n, right, into L10R. Means this L10R, L10H is rated bearing life in hours, right, and we are dividing it with 10 raised to 6 because L10 is the revolution, or we can say millions of revolution, right, that L10 is given in million of revolution. So this L10 into the 10 raised to 6 will be equal to this 60 into this n is the speed of rotation in RPM, right, n is the speed of rotation in RPM, right, and this L10H is a rated bearing life in hours, right. So this is how you can have your this L10 live, right, in million revolution, right. So from that rated bearing life in hours, you can convert it into million of revolution, right. So if we have this much of understanding about this particular bearings, and we can, I guess, go for solving the simple numerical, right, one by one we will go. First is, in a particular application, the radial load acting on a ball bearing is 5 kilonewton, and the expected life for 90% of the bearings is 8000 hours. Calculate the dynamic load carrying capacity of the bearing when the shaft rotates at 1450 rpm. So can you try this one? Hello.
Yes, sir.
So here what is given is this Fr is 5 kilonewton, right, then this L10H is given as 8000 hours, and this N RPM is 1450 rpm, right. Okay, So now from this you can calculate this L10 life in million of revolution, right? As we have seen lastly, that L10 is nothing but 60n L10h upon 10 raised to 6. So
696.
sorry,
696 million of revolutions.
yeah, correct. So it is almost coming around 696 million revolution. Right, and then dynamic load capacity, that is C, right? So what is the relation between that C and this L10? The C is P L10 plus 2 1 by n, right? Here it is ball bearings, so it will be P L10 raised to 1 by 3. Yes or no?
Yes, sir.
Okay. So what is C?
44.31 kilonewtons.
44.31 kilonewton. Yeah, so it is almost 44.31 kilonewton. Okay. So once you have calculated this, then you can see this one, right? Second one, a taper roller bearing has a dynamic load capacity of 26 kilonewton. The desired life for 90% of bearing is 8000 hours and the speed is 300 rpm. Calculate the equivalent radial load that the bearing can carry. So now how can you approach this particular problem? Here dynamic load capacity is given, right? Here see the radial load acting is given, right? And here dynamic load capacity is given, right? So the C is equal to 26 kilonewton, right? Then again L10H is similar, right? That is 8000 hours. Then N is 300 rpm. So from this, first you can calculate million revolution, right? As previously you have calculated. So what is this? Sixty into 300 into 8000 by 10 raised to 6, right? So what is that?
144.
Yeah, so it is around 144 million revolution. Then what you are asked in this case is that P you need to calculate, right? That radial load. So how can you calculate that radial load? You know that C is equal to P L10 raised to 1 by n. Here n is 10 by 3, right? Because it is roller bearing, correct? Okay.
Yes, sir.
So 26 into 10 raised to 3 is equal to P into this 144 raised to 0.3. This will give you P, right? So what is P?
Is it 4.96 kilonewton?
No. Anyone else? It is 26,000 divided by 144 raised to 0.3.
5.85
Yeah, it is.
kilonewton.
It is around 5.85 kilonewton. Right, it is around 5.85 kilonewton. Okay, so this is how you can have idea about this dynamic load capacity and this load acting on your bearing. Right now, once you have idea about this rated life and what we can say, this relation between this dynamic load carrying capacity and that radial load acting on your bearing, then sometimes it is required to consider this case as it is mentioned, right, the design for cyclic loads and speed, right. So for that, actually what you need to do is you need to consider that different loads, right, for different amount of time acting on your bearing, and that too at different speed. So if this kind of situation is there, then what we need to do is, first we have to have idea about all the different loads, right. So suppose that for P1, that we are assuming that life is L1. So for L1 we can write like this, if we consider ball bearing, right, then it will be this C by P1 plus 10⁻⁶ revolution, right. So this life would be this L1 if only P1 is acting, right, on the bearing, right. Similarly, this in one revolution, the life consumed is considered as 1 upon L1, right, in one revolution, right, in one revolution, right, the life consumed is this 1 upon L1, right. So if we consider that life consumed is 1 upon L1, then it is actually given by this P1 cube upon C cube into 1 upon 10⁻⁶, right. Now if the first element is consist of n1 revolution, right, then the life consumed by the first element is then given by this n1 P1 cube, right, upon 10⁻⁶ into C cube. So the same way you can go on adding the life for that other RPMs. For n1 RPM, the life consumed is given by this n1 P1 cube upon 10⁻⁶ into C cube. Similarly for n2, it is n2 P2 cube upon 10⁻⁶ into C cube, and so on, right. So here in our case we are having this three different loads, right. So it will be again that n3 p3 and all, but it can go up to n number of load up to which it is acting for different amount of time, right. Now this all different load and different RPM can then be equated to a particular equivalent load, right. So we can assume that equivalent load, right, for the complete duration, right, and then equivalent RPM n for the complete duration. So basically then this can be equated to that equivalent load and equivalent RPM, right, like this. So where this particular n is nothing but sum of all the RPM for different amount of time, whatever n number of different types of RPM, right, or different amount of RPM was there, right. So as we have equated here this different life, right, because at different load and for different RPM there will be different life. So if we are equating this to this equivalent life, then what we are going to end up with is this 10⁻⁶ into C cube will be cancelled out, right. So if that will cancel out, then what we will left with is this n1 P1 cube plus n2 P2 cube plus n3 p3 cube, right? In our case actually it is n3 p3 cube, right? So yeah, this n3 p3 cube can then be equated to this n pe cube, right? This npe, if I write that e more clearly, and then this npe cube. So from this actually we will be able to calculate that PE or equivalent load, that can be then mentioned as this one, right? N1 P1 cube plus N2 P2 cube plus N3 P3 cube divided by N1 plus N2 plus N3, because as we know this N is nothing but the sum of all this RPM, right? So once you have this relation, then you will be able to calculate this equivalent load, that is PE, right? Now it is used when we are not having any variation, right? Otherwise if it is if that load is varying with respect to time, then we need to integrate that, right? So if that load is going to vary with time, then we would have integrated it, right, like this 0 to n p cube dn, right? Similarly this 0 to n dn, right? And then this whole is actually raised to 1/3, right? So this is how you can come up with equivalent load. So now having this idea about this cyclic and fatigue loading, then you can try and attempt this particular question. What this question says is, a single row deep groove ball bearing has a dynamic load capacity of 40,500 Newton and operates on the following work cycle. The first is radial load of 5000 Newton at 500 RPM for 25% of time. Then radial load of 10,000 Newton at 700 RPM for 50% of the time. And then radial load of 7,000 Newton at 400 RPM for the remaining 25% of time. So you need to calculate the expected life of bearing in hours. So how can we approach this, right? So in that case we need to calculate that equivalent load, right? Because you are given that this 40,500 is dynamic load capacity, that is C, right? And you are provided with the different RPMs for different load, right? So from that you need to come up with equivalent load, so that you will be able to calculate first that millions of revolution, right, equivalent life. And once you calculate that equivalent life, then you will be able to calculate it in hours by that relation, right, that L10 is equal to 60 n L10s divided by 10 raised to 6, right? So how you can proceed is, you can actually have the table, right? So let us have the table showing that element number means what are the different number
Sir?
of loads.
Excuse me, sir.
Yes,
N1, N2 are the individual times, no, sir, time intervals.
sorry, n1 n2.
N1, N2 are individually how much time it is running for.
It is RPM actually, right? So we are going to consider the time also, right? So here it is mentioned that 25% of time. So what we are going to consider is, let us say it is running for 1 minute, then 25% of time is 0.25 minute, right? And 50% of time is 0.5 minute. and again remaining is 0.25 minute, right? So if we first note down the load, right, that is this 5000, then 10,000 and 7,000, 5,000, 10,000 and 7,000, then duration, right, element time, that is 0.25 minute, then 0.5 minute, and again 0.25 minute, right? And speed is mentioned in RPM as 500, 700 and 400, right? Now this revolutions n in element time, right? It means that we have provided a particular amount of time for this load, right? So, and the speed is 500 rpm, so number of revolution during this first cycle will be this 500 into this 0.25 minute, that will be 125, right? So in that case, yes, as you were telling, that n1 is representing the duration for which that particular amount of speed will be there, and at that particular load it will be there, right? So someone has recently asked, right? So it is, yes, the time only. Okay, are you there?
Yes, sir.
Yeah, so that is 125, 350 and this 100. So this is the number of total revolutions, right? Because this is the speed and this is the duration of that particular loading. So the number of revolution will be the speed into the time for which the speed is there. So 500 revolution per minute is there for 0.25 minute. So during that time 125 revolution will be there, right? So the total number of revolution will be 575, right here. Is it correct? Hello.
Yes, sir.
So here actually this particular is that a time element, right? But when you convert it into this revolution, then here this n1 represents this revolution during that particular time. Is it clear?
Yes, sir.
Okay, so once you have this data, then you can now calculate this PE with this equation which we have just derived, right? This PE equal to this N1 P1 cube plus N2 P2 cube plus N3 P3 cube divided by N. We have calculated the total N as 575, right? So you can tell me what is this PE. Can anyone tell? What is this PE?
8860, sir.
Yeah, it is almost around 8860,
Newtons.
right? 0.6 Newton, right? So once you have this PE, then you can calculate the life in million of revolution with this relation. Let's see, by PE was to 3, because it is ball bearing, right? So what is that? C you have already, right? That is 40,500. 40,500 divided by this 8860.6 is to 3. So what is the answer?
96.
It is almost around 96 million revolution, right? So once you have this, you can calculate that L10 hours, right? How you will be able to calculate that? L10 hour is this n into 16 to L10h divided by electricity.
Sir,
So yeah,
in calculating PE, N1 is 125
yes, n1 is 125,
and P1 is 5000.
p1 is 5000. Yes.
Okay, sir.
So from this now we will be able to calculate
Excuse me, sir.
yes.
Sir, actually, each part of the term represents like how much amount of revolution it is actually contributing.
Yes, that n1 is actually the amount of revolution has occurred while that p1 load is acting. That is what it is.
So what is the speed in the rated line?
Sorry,
In the Elton formula, what is the speed, sir? M?
n is given, I guess, right? That 575 we have calculated, right? That
Okay,
total
okay.
total revolution we have calculated as 575, and we have assumed life of 1 minute, so 575 is your n here. Okay.
Yes, sir.
So now what is your answer?
2783.
2780.
Okay,
Note.
so by taking that 96, it may be 2783. But here what should be done is actually, here instead of directly going to this round figure of 96, you may have got something different, right? So go or stick to those decimal places whatever you are getting, right? Because here it is a million revolution, right? So it is multiplied with 10 raised to 6. So it is advisable not to directly round it off to the next one. Is it correct? Are you getting what I'm trying to say?
Yes, sir. It is coming 95.51 million revolution.
Yeah. So better to go with that,
2 7 hours, sir.
right? So better to go with this, right? Because it is in
Mm.
terms of this millions of revolution. So if you go with this, then here again your this L10H may be modified.
2767, sir.
Sorry.
2767 hours, sir.
Okay, so it is roughly around the 2767, right, or 2768. Okay, so once you are done with this, then we can go to the next one, that is the sliding contact bearing, right? So in sliding contact bearing, we are having this hydrodynamic lubrication or hydrostatic lubrication, right? Generally we are having this kind of lubrication in case of the sliding contact bearing. So first, if we see this hydrodynamic lubrication, right, then in this what is going to happen is, as shown in the figure, at the beginning when journal is at rest, there will be contact between this journal and this particular what you can say, this bushing, right, inside which it is there. So once it starts to rotate, then there will be a generation of this film of that lubricating oil, right, as it is mentioned here in figure B. And at high speed, this is this oil wedge or this kind of wedge shape is created at higher speed, right? So at full speed there will be enough separation is achieved as it is mentioned here, right? And the pressure distribution in hydrodynamic bearing is given by this particular profile as mentioned here, right? So in case of the sliding contact bearing, this hydrodynamic lubrication is actually behaving as mentioned in this given figure 16.1, right? So once you have idea about this hydrodynamic bearing, then this hydrodynamic bearing can be this full bearing or partial bearing. As you can see here, this is full bearing, right? That full journal is inside this, right? While here only that partial journal is there, right? So in that partial what you can say this surface or that bushing is provided, right, to this journal. So here in this case only it is always, I guess, less than 180 degree in case of partial, right? And most of the time it is around this 120 degree as mentioned in this figure, right? So this is how full and partial bearing is mentioned in case of this hydrodynamic bearing, right? Then in case of hydrostatic bearing, as we can see in this particular figure, in this hydrostatic lubrication we can provide this oil through a pump, right, between the journal and this bushing. So what happens in case of hydrostatic lubrication is there is no need, right, of be dependent on the speed of journal, right, for the amount of lubrication. In case of hydrostatic lubrication, this particular this film thickness and all can be maintained at lower speed also, because it is maintained with the help of some external pressure. As we can see, it is coming from a pump, right? So in hydrostatic lubrication it can be maintained like this, right? So this is something I guess related to that footstep bearing and collar bearing. I guess this is some thrust bearing, right? Here you can see along the line axis of shaft the force is applied, right? So this is types of thrust bearing as it is mentioned here, right? Now in case of lubrication or boundary lubrication, this film is very thin. So what happens is at some place you may have that metal to metal contact, right, as it is mentioned here at place A, while at other places this cluster of molecules is there as mentioned at B. So in this case particular a type of lubricant is used, right, which is having this polar molecules. Polar molecules means that certain particular what you can say lubricants, this positives and negative ions are separated, right? So this is how we can achieve those kind of polar molecules in certain lubricants, and those lubricants are used in case of this kind of boundary lubrication, right? So this is how you can have that boundary lubrication. But in that case, as you can see, somewhere this metal to metal contact will be there, right? So now in case of understanding this sliding contact bearing, as there is a lubricant film is generated, right, between that journal and that bearing surface. So it is important to understand this concept of viscosity. I guess this is you all have come across in your fluid mechanics, right? But here if we again try to understand this, then you can see if there is fluid, right, so viscosity is basically it is going to resist the motion, right? So as you can see if we consider two plates, right, a plate is stationary and another plate is moving, right, and we have a fluid, right, between these two plates, then what happens is this uh, stationary plate is having an adjacent layer of molecules which is not going to have motion, right, it is almost steady. And what happens is the moving plate will have that molecules in motion, and this particular velocity with which this plate is moving will be imparted to the molecules, right, which is proportional to the distance from the stationary plate, right. So basically what we can do is we can represent it this particular what you can say, this shear stress, right, actually as per the Newton's law of viscosity, this tau is proportional to this, what we can say, this velocity, right? So mu is that proportionality constant, right, tau is proportional to this du by dy, right. Du is the change in velocity with this y is actually this h. Actually here you can also consider it du by dh instead of that from this particular figure you can actually consider that this tau or the shear stress is proportional to this du by dh change in the velocity with respect to the distance from the stationary plate, right. So now if you further write this stress in terms of this load applied and this area, then you can write this stress as E by A is equal to this du by dh, and here your proportionality constant is actually the viscosity. So P by A is equal to this mu du by dh. So this is how you can have the relation between that load and this velocity, right. So you can define viscosity as this mu is equal to this P by E, right, into this dh by du, right. So if you write for a particular point, then you can consider it as P by A into h by u. If you are considering any point at distance h, right, this may be the full distance h, right, then the velocity may be the actual velocity of the plate with which it is moving, right. So at that particular point this mu can be represented as P by A into h by u, right, and the unit is this Newton second per mm square, right, this Newton second per mm square. So basically megapascal into second. So this is how this viscosity is there for this particular fluid, right. Now if we go for this Petrov's equation, then again there are some assumption, right, that the shaft is concentric with bearing and the bearing is subjected to light load, something like that, right. So if we are going to derive this particular Petrov's equation, then we can first note down some of the things like r is the radius of the journal, right, then L is length of bearing, L is length of bearing, then C is radial clearance, right, and and this ns is journal speed, right? Which is in revolution per second. Right, now the velocity at the surface of the journal, right, velocity at the surface of the journal is given by this 2 pi r into ns, that is pi dn, right, basically. So this is given as 2 pi r into ns. Now Newton's law of viscosity we have already mentioned as this p is equal to mu a u by h, right? Now this p is tangential force as we know, and then this area of journal surface here, if we write P is tangential force, that we know, right? But the area of journal surface that is pi dl, that is 2 pi r into l, right? That is surface area. Then surface velocity, as we already mentioned, 2 pi r ns, right? And then h is nothing but the distance between journal and bearing surface, that is clearance, right? So this h is nothing but c, right? So now if you put all these values into this equation, right, this p is equal to mu a into u by h. So P is equal to mu a is 2 pi r l, right, that pi dl. Then u, as we have mentioned, that pi dn, that is 2 pi r ns, right, and h as we have considered as c. So if you give simplification, then it is 4 pi square r square l mu ns pi c, right? 4 pi square r square l, right, into mu, right, into ns divided by c, right? So now once you have this p, then frictional torque you can consider as p into r, right? Once you have this load, then frictional torque T can be p into r. So p into r means that r cube will be there, right? 4 pi square r cube mu ns l divided by c, right? Now if you consider radial load, right, then this radial load acting on the bearing, right, then what you can consider is, because of as it is mentioned in the figure, right? So we are talking about this particular radial load, right? So if you consider that radial load W, right, then pressure because of that radial load can be given as that P is equal to this radial load upon projected area of bearing, right? Projected area of bearing is simply that 2r into length of the bearing, means diameter into length of bearing, that is projected area. So because of this particular W, what we are having is that bearing pressure, right? This unit bearing pressure we can define with this radial load W. This bearing pressure P is equal to W upon projected area. So this P is equal to W upon 2RL. Right, 2RL is nothing but the diameter into length, right? So from this actually you can write this W is equal to this P into 2RL, right? So once you know this, then the frictional force will be that F into W, right? And frictional torque will be that F into W into R. So as you have this W as radial load, then Fw as frictional force, right? If you have that W as radial load, then Fw will be frictional force, right? This will be frictional force, and because of that you will have frictional torque, that is this Fw into R. So this F into R as it is, and W we have written as P into 2RL, right? So P into 2RL, so if we further simplify, then it is P into 2R square L, right? Like this. So once you have this frictional torque, then we have also calculated frictional torque earlier, right? So you have this frictional torque, right, like this. Right, and you have also derived frictional torque earlier, right, like this. So once you have both of this frictional torque, right, we can equate this to, right? So if we equate this to, then we can have that value of this F, right? That is nothing but coefficient of friction. So once you equate this to, it is F into this F into P 2R square L will be equated to this 4 pi R cube, 4 pi square R cube L mu n s upon C, right? So now from this you can write this F is equal to 2 pi square R by C mu n s by, right, R by C mu n s by P, right? So this is known as Petrov's equation, right? So this is how you can have your Petrov's equation, right? And there are two important dimensionless numbers, right? That R by C and mu n s by P, right? That governs the coefficient of friction, right? So from this particular thing, one more important thing is this Mackey's investigation. So what this Mackey brother has done is they have investigated that how this mu n by P is affecting this thickness of the film, right? Lubricating film. So what happens is, as you can see in the figure, this is the curve, this mu n by P curve, right, against this coefficient of friction. So at the beginning there is metal to metal contact, right? Somewhere in this thin film region there exists some particular metal to metal contact, but when we go in this thick film region or this stable region, at that in that region this particular metal to metal contact can be avoided, right? So the AC line is the transition line between this thin film and thick film lubrication, right? So what is this C, right? Point C. At point C, this particular bearing characteristic number mu1 by P is considered as the bearing modulus. Bearing modulus, right? So the minimum value of this this minimum value of this bearing characteristic number should be equal to K in order to avoid metal to metal contact, right? So generally it is kept 3K so that it is ensured that there is no metal to metal contact while operation is going on, right? So generally this bearing modulus is kept that high, right? 3K almost, in order to avoid this metal to metal contact, right? But in BC region there is thin film, right? So there may be some metal to metal contact, but in CD region it can be avoided, right? So this is how you can have this sliding contact bearing and the importance of this thick film and thin film lubrication, right? And difference between hydrodynamic bearing and hydrostatic bearing, right? So once you have idea about this, then we can see some of the questions from GATE, right? If you see this question, then which one of the following is a criterion in the design of hydrodynamic journal bearing? So basically that what we have discussed is known as the Summerfield number, I guess, right? That particular Petrov's equation what we have seen in that number is known as Summerfield number. So here your answer will be this Summerfield number, right? So this particular it is actually a theoretical question, right? So let us go to the next one. This is the question from GATE 2007, right? It says that a ball bearing operating at a load F has 8,000 hours of life. Now the life of bearing in hours, right, when the load is doubled to 2F. Can you try this question?
1000 hours.
Sorry?
1000, sir.
1000. Anyone else? Sorry? See, this L10 we have considered, right? What is that L10? Anyone can tell? What is that L10?
In revolutions.
Yeah, it is that C by P raised to n, right, into 10 raised to 6 number of revolution. Yes, is it correct? Yes. And in case of the ball bearing, this n is 3, right? This 10 raised to 6 I have not mentioned because we were writing that revolution as million revolution. Is it okay? Hello.
Yes, sir.
So now what we are given is this particular this in hours of life it is mentioned, right? So what basically given is this load is given, right? So in first case, actually it is proportional to this, right? If we go for that hours life, let me write that. Actually in that case it is this N60 L10H upon 10 raised to 6. So actually there is no difference of L10 and L10H, right? This C by P will be having the same proportion as we are writing here. So L10H also can have this proportion, inverse proportional to the P1 raised to 3. Are you getting what I am trying to say? Anyone?
Yes, sir.
So this
So
L10 H1 is proportional to this 1 upon P1 cube, right? So if we take the ratio of L10 H 1 upon L10 H 2 is equal to this P2 by P1 cube, correct? Right. So what are we given is this P1 is F and P2 is 2F, right? And we are provided with L10 H1. So now if we put values, then what is L10 H1? It is 8000, right? What you need to calculate is L10 H2, right? Equal to P2 is 2F, P1 is F, just to 3. So L10 H2 is equal to 8000 by 8. Yes or no?
yes, sir.
So this way L10 H2 is equal to 1000. So this is how you will get this. So then the next is a natural feed journal bearing of diameter 50 mm and length 50 mm, operating at 20 revolution per second, carries a load of 2 kilonewton. The lubricant used has a viscosity of 20 millipascal second. Then the radial clearance is 50 micron. The Sommerfeld number for the bearing is, so what is Sommerfeld number? Actually this Sommerfeld number is this R by C square into mu n by P, right? So this P is bearing pressure on projected area, right? It is bearing pressure. Right, on projected area. Right, then n is the number of revolution per second. This is revolution per second. Then mu, you know, viscosity, right? And C is clearance, radial clearance, right? R is radius of journal. Right, so this actually from Petrov's equation only this has come. If we go and check this one, then from this only it has come, right? This Sommerfeld relation. R by C square, here it is 2 pi square R by C mu n s by P, right? So from this only this Sommerfeld number has come. So I guess you can try with this one, right? This bearing pressure is, as we have calculated, that W by DL, right? 2 pi RL we have written. So this bearing pressure is W by dl. W
Is it
given,
0.125?
sorry,
Answer, sir. 0.125?
yes, correct. So this bearing pressure is this W by d into L, where this W is given as 2 kilonewton, right? 2000 divided by this diameter and length both are 50. So P is this 2000 divided by 50 into 50, right? And what else? Radius is 25 and clearance is given as 50 micron, right? So if you put all the values now, if you simplify this 2000 by 50 into 50, then it will be 20 by 25, right? 20 by 25 is 4 by 5, so 0.8. So now S is equal to 25 by radial clearance is 50 microns. So if we convert it into mm, then 15 to 10 raised to minus 3. So this whole square, right, into mu n by p, right? Mu is given as, let us see what is mu, is given as this 20 millipascal second, right? Mu is 20, n is 20 revolution per second, and p we have calculated as 0.8. So it is 20 into 10 raised to minus 3, right, divided by 0.8. So 0.8 into 10 raised to 6, because we are considering it is in Pascal and it is megapascal, 0.8 megapascal, right? 0.8 Newton per meter square is 0.8 megapascal. So as we are considering it in Pascal, it will be 0.8 into 10 raised to 6. So this is how, once you simplify this, you will get 0.125. So is it clear? Hello, is it clear? Anyone? Okay, so let us go
Yes,
to
sir.
the next one. That is, a journal bearing has shaft diameter of 40 mm and length of 40 mm. The shaft is rotating at 20 radian per second and viscosity of the lubricant is 20 millipascal second. Clearance is this. The loss of torque due to the viscosity of the lubricant is. So can you try this one? So here you can start with calculating the torque, the tau, right? The stress. The stress can be calculated with this mu v by c, because it is mu du by dy. Du is this velocity and dy is this clearance, right? So mu du by dy. So mu is given as again 20 into 10 raised to minus 3 millipascal second. V is r omega, right? So r is 20 mm, right? And this omega is again 20 radian per second, divided by this is 0.02 mm. clearance is. So all these things are in meter, right, because Pascal second is there, right, in this viscosity. So tau is 400 Newton per meter square. Is it correct? Right? Are you getting this? Stress, shear stress. Anyone? Hello?
Yes, sir.
Okay, so once you get this stress, then you can calculate the force, that is stress into area. Area is, what will be the area over which it is acting? That is pi
Projected area.
pi dl. Area is pi dl. 400 into pi into diameter again 14 to 10 to the minus 3 into length again 14 to 10 to the minus 3. So that will be the force. So what is force? Can anyone? If we can
B.
cancel
0.64.
point
2 point something.
okay, so 4 into 4 into 4, that is 64, right? So 640 into 10 raised to minus 3 is 0.64 into pi, that will be force. Now what you are asked is the loss of torque, right, due to viscosity. So this torque will be this force into radius. Radius is 20 mm. 20 mm is 20 into 10 raised to minus 3, right? So now tell me, what is this torque? What is this torque?
0.04.
Yeah, it is 0.04 Newton meter. Right, so this will be your answer. Okay, then next is this one. A lightly loaded full journal bearing has journal diameter this, then journal bore of 50.05 and bush length this, rotational speed of 1200 rpm and average viscosity of the liquid lubricant is 0.03 Pascal second. The power loss, I guess it is similar. Can you try this? You will be able to calculate this by yourself, I guess. Yes or no? Here U is pi dn by 60, right? I am telling you U is pi dn by 60. The same way you can calculate, which we have done previously, right? And clearance is this 50.05 minus this 50 divided by 2, because we are going for radial clearance, right? So then again you can follow the same thing. First you can calculate your shear stress, this, right? Tau is equal to mu du by dy. You have mu as 0.03 Pascal second. This u and y you have already calculated, right, from these two equations, right? You can calculate this, and then you can have this tau. Then again same, that force you can calculate with this tau into pi dl, right, projected area. Then once you have force, then again torque will be this force into T by 2, right?
So can you kind of explain this du by dy part also?
Sorry?
How it is
Sorry?
du by dy?
Du by dy?
Basically, u is calculated using pi dn by 60.
Yes, yes. Yes. Then
And then y is the thickness.
why is the radial clearance?
Yes.
Right. So this way you can again calculate the torque, right? But here they have asked the power loss in watt, right? So actually whatever we were calculated previous question, that is in Newton meter, right? So there is a relation, right? So if you are writing it 2 pi nt by 60, right? So in previous question it was the torque, I guess, if I am not wrong. Then they have asked that that loss of torque, right? So that is why we have this Newton meter, right? Now they are asking for power, so we need to go for this power is equal to this 2 pi nt by 60. So I guess you will be able to do it, right? You can quickly calculate and tell me.
Is it A?
Yeah, it is A only, right? So I guess you will be able to do this, right, if you follow this. Should I go to the next question then? Yes or no? Hello, anyone?
Yes, sir.
Okay, so let us go to the next one. It is also simple, right? Two identical ball bearings P and Q are operating at loads 30 kN and 45 kN. The ratio of the life of bearing P to the life of bearing Q is. So I guess this again you can go for this. I'll tell P proportional to this 1 upon P cube. Right, here it is force in P, right? Then I'll tell Q is again 1 upon P of Q, right? So I'll tell this P and Q will be equal to force in Q divided by force in P Q, right? Because it is ball bearing, this N is 3. Here P and Q are that 45 by 30s, I guess. So tell me, I guess.
B.
Sorry?
Answer B.
B, yeah. Because 45 by 30 is 3 by 2 raised to 3, right? So that is 3 cube of 3 divided by cube of 2, so it is 27 by 8. Okay. Then next is this one. A hydrodynamic general bearing is subjected to 2000 Newton load at a rotational speed of 2000 rpm. Both bearing bore diameter and length are 40 mm if radial clearance is 20 micron and bearing is lubricated with an oil having viscosity 0.03 pascal second. Sommerfeld number. You can calculate this, right? Because now you know what is the Sommerfeld number, right? What is Sommerfeld number? You have calculated, right? Can anyone tell? Anyone?
R by C bracket square into mu ns by P.
Right? So what is R here? 20 mm, right? Diameter and length are given as 40 mm, so radius is 20 mm. Then clearance is 20 micron, So 20 into 10 raised to minus 3 mm, right? Then mu is 0.03. Then here RPM must be in seconds, so it is 2000 divided by 60 because it is given in revolution per minute. So it is 2000 by 60. And this bearing pressure, so actually this you need to calculate, I guess. P is equal to,
Sir, answer is 0.8.
answer is 0.8, yes, correct. So you need to calculate this P, right, bearing pressure, that is W by A. This bearing pressure P is W by A, where W is given as 2000 Newton. Area is diameter into length, that is 40 into 40. So it will be actually this 40 into 40, I guess we need to consider it as into 10 raised to minus 3, right? So 10 raised to minus 6 if we go for both. Then
Sir,
yeah,
sir, actually, this units is a bit struggling, sir. Actually, which unit should we take for length? It's always meter only.
sorry.
For all the lengths, diameter, length, clearance, everything we will take in meter only, right?
No. So see what we have done is this radial, this radius and this radial clearance, both we have taken in mm. See here, because it is going to be cancelled, right? So for this ratio R by C, we have considered both in mm. When we go here, this mu is in Pascal
So
second,
usually,
so that is why we are going for meter. So here, that is why I have converted this 40 into 40 as meter square. So that is why I have multiplied here with 10 raised to minus 6. So it will be 1.25 into 10 raised to 6. Right, I have converted it into Newton per meter square because here Pascal is Newton per meter square. Did you get that?
yes, sir.
So here it is 1.25 into 10 raised to 6. Now when you simplify this, it will be 0.8. Is it correct?
Yes.
Okay, so the next is this ball bearing rated by manufacturer for a life of 10 raised to 6 revolution. Catalog rating for particular bearing is 60 kilonewton. The design, if the design load is 2 kilonewton, the life of bearing will be P into 10 raised to 6 revolution, where P is equal to, see, how can you approach this problem? Can you try this one?
So catalog rating means, is it C?
Sorry,
Catalog rating of particular bearing means.
it means that that capacity, that dynamic capacity, we are having that C, right?
Okay.
Right, that is C by P raised to N, right? So that,
Sir, answer is 512.
sorry,
512 answer.
answer.
Hmm?
192, sir.
Anyone else?
512.
Yeah, it will be 5 and 2 because C is 16 kilonewton, P is 2 kilonewton, right? So it is the 16 by 2 raised to 3. Simple.
Oh, sorry, the calculation.
16 by 2 raised to 3. It is simple, right? Straightforward because it is ball bearing. So N will be 3. So that is why it is 512. Into 10 raised to 6, it is already mentioned, right? So that is why it is 512. Correct? Okay.
Sir.
Okay, so the next is for ball bearings, the fatigue level measured in number of revolution and the radial load F are related by FL raised to 1 by 3 is equal to K, right, where K is a constant. Now it withstand the radial load of 2 kilonewton for a life of 540 million revolutions. Now the load in kilonewton for a life of 1 million revolutions. Can you try this one? So it is also straightforward, right?
13.2.
I don't know anyone else, because FL raised to 1 by 3 is constant, right? So for F1 L1 raised to 1 by 3 is equal to F2 L2 raised to 1 by 3. This F1 is given as 2 kilonewton, right? And L1 is given as 540 million revolution, right? Equal to, you are asked for 1 million revolution, right? So for 1 million revolution, what will be the F2? So what is that?
Sir, regarding the power 1 by 3,
Sorry?
regarding the power, sir, 1 by 3,
Huh.
should we take it as 1 by 3 itself, or can I take it as 0.3? Because if I take it as 0.3, I will get around 13 answer. And if I take it as 1 by 3 whole, it will come around 16.
Actually 1 by 3 is better, because 1 by 3 is 0.33333, right? So 1 by 3 is not 0.3 actually, right? Are you getting?
Yes, sir.
So it is better to go with 1 by 3. So it will come around some 16.28 kilonewton or something like that, right?
Yes, sir.
Okay. So let us go to the next one. Right, which of the bearing should not be subjected to a thrust load? Can anyone try this one?
C. Chennai.
Yeah,
Identical roller bearing.
correct.
Bearing.
This cylindrical straight roller bearing cannot take thrust load. Otherwise, this deep groove or this angular contact or this tapered roller can take the thrust load. Correct. Right, and the last one is a self-aligning ball bearing has a basic dynamic load rating, right? For 10 raised to 6 revolution is of 35 kilonewton. Now if the equivalent radial load on the bearing is 45 kilonewton, the expected life in million revolution is. So can you try this? So C is given as 35, right, and equivalent radial load P is given as 45.
A.
Yeah, correct. So anyone else?
Sir, A.
Yeah, it is below 5, because this L90 or L10 will be C by P raised to 3 again, because it is ball bearing, right? So C is 35, P is 45. So this will come around 0.4705, right? Okay, correct.
Yes, sir.
So this is how you can come up with your answer as A only, right? It is below 0.5. Okay, so today we will keep up to here.